Hi everybody. In this video I'm going to talk about the solution to the Brachistochrone problem. If you remember, this was a challenge problem put out by Johann Bernoulli, and he worded it in a way to tempt Newton. He was really challenging Newton, and of course Newton solved it the night that he got it. Bernoulli was not the first one to think of this problem. Even Galileo had worked on it in as early as 1638, and he talked about it in one of his books. There were 5 solutions to this challenge problem, one given by Newton, one by Jacob Bernoulli, Johann's brother, Leibniz, of course, and the Hospital also gave a solution. Of course, Johann Bernoulli had a solution before he actually published the challenge. And on the screen I have actually a diagram from Newton's solution. Newton sent his solution to the Royal Society in London, so to the president of that society, and had it published. So here's point A, here's point B in a uniform gravitational field, and this is Newton's solution, which is, the curve is called a cycloid. And we'll talk about that. I'll tell you right away what your textbook gives you as a solution. This is the x and y parametric equations for the cycloid. And there's this plotted y versus x here for these equations. Now, I'll show you, we'll work through it together, and I'll show you we'll get this solution. But here is that solution plotted, so you can see it's the same. Okay. For both of these, I let a here equal 1, and I plotted from theta is 0 to 2 pi. So. Then also in this video we'll talk about the law of refraction. We'll develop this law of refraction from light going in one medium to another based on Fermat's principle. Fermat's principle, again to remind you, is that light will travel a path that minimizes the time between A and B. And we talked about this problem. I set it up as a lifeguard going from A in sand and then crossing over a boundary into water to get to B. So that's what we'll do. So let's get started. Okay. So just to remind you, when we're using Euler's equation, we have something that I'm calling J here that we want to minimize. And we can write it like this from some x1 to x2. So we're integrating over x, and we identify what's in here as the functional. And this is Euler's equation that is necessary for us to have a minimum j. So we went through that in the previous video about how to derive that, and we used it for at least one example. Now, I also remind you that what you're doing here is, by using this equation, we're solving for y as a function of x. That's what we're wanting. There might be a case, for example, in this next example, where we want to find instead x as a function of y. We want to think of x as the dependent variable on y. And if you do that, you can show easily that the equation would change to this. Euler's equation. Okay, so we would have, in this case, j is equal, write it like this, where we'd have x prime and in fact that's what we're going to do when we do the Brachistochrone problem. So to remind you about the Brachistochrone problem, we have B, that can slide down a wire. It's here at A. It's in a uniform gravitational field with gravitational acceleration g, and it's going to go down to B, and we want to find the path, a formula for the path. So I'm going to call this direction x, and we'll call down y. So let's look at a little segment on this path length, and let's call that ds. So the little arc length, we can write ds squared as dx squared plus dy squared in our coordinate system. Or we can write it like this. And you see what we're doing now, we're going to do quite often. And then this is the square root. I'm going to extend this down here. Now what I could do is take this and divide by dy squared and multiply by dy squared. There's nothing wrong with doing that. And I have dx dy squared, so that's going to be x prime squared. X prime is going to be dx dy. Plus, and this is all under the square root, dy over dy, so that's 1. And then I have dA dy squared under the square root, so that's just dy. I'll pull that out. So I could have written that a little nicer. It's going to look now like this. Okay, so what is it that we're wanting to minimize? We're wanting to minimize the time. Time of travel between A and B. A and B. So how do we write the time? Let's write a little bit of time as we travel. That little arc length ds, that little length. How much time does that take? Well, the distance divided by the speed gives you the time. So I can write time as if I integrate that. Now I got to do something for v here. But you can see I'm writing this now. I say y1 to y. This is some final y and x. And this was our initial y1, x1 up here. Okay. Now, I need it's not going to be a constant speed as it falls through here. But I can use my current knowledge, so I can use conservation of energy. It's in a uniform conservative gravitational field. So I'll start out here at rest. So I'll say it starts at rest. So it has 0 kinetic energy. I'm going to say the potential energy is 0 up there too. So what I'm going to have is 0 energy total to start with. When it gets down to here, it's going to have 1/2 mv squared of kinetic energy minus mgy of potential energy. So looking at this equation here, this is going to imply that v is equal to this square root of 2gy. So what do I have now? I have time is going to equal, going from y1 to y, square root of x prime squared plus 1 over the square root of 2gy dy. So this is my functional. So it does have y explicitly in it now, and x prime, no x explicitly in there. So here is my Euler equation. that's necessary to have a minimum, and we'll see what happens. So first what I'm going to do is I'm going to show you how I would go about solving this, and then we'll talk about what they do in your book. Okay? All right. So starting with this up at the top. So I don't have x explicitly in this, so I'll have df dx is 0. So this must equal 0. So let's look at this. Let's look at the partial of f with respect to x prime. Here's f. So when I take that derivative, of course, this 2gy, nothing happens to that. And I take the derivative of the square root up here at the top, and I'll get 1/2 1 over square root of x prime squared plus 1, plus 1. And then the derivative of what's in here with respect to x prime, so that's going to give me 2x prime. So I get x prime over the square root of x prime squared plus 1 times the square root of 2gy. So the fact that this is 0 Okay, so if this is equal to 0, what that means is that x prime over square root of x prime squared plus 1, square root of 2g, square root of y, I'm pointing that out for a reason, is a constant. And why I pulled the square root of 2g out is because that's a constant too. I don't want a bunch of constants roaming around here, so I'm going to merge that in with that constant. So what I'm going to have is this. And this is a constant, and I'm going to call that constant 1 over 2a because your book does so. Okay, so a is a constant too. Okay, so remember this comes from the Euler equation, and now I'm going to solve for x prime, which is dx dy, in this case, is equal to, once I solve for that, I won't go through the algebra, I'll let you do that if you want to check me. I get this. So that means dx is equal to this. And if I integrate, I get x equals this plus an integration constant. Okay. y1 to y. So we need to do this integral. So that's the next step. Okay, so now we got to do this integral. Now one way you can do it is you can look in integration table or try to have an online integrator do it for you. I'm going to show you how I would do it, and it requires, first I'm going to do a little substitution, then I'm going to do trig substitution. So 2 substitutions here. So I'm going to let w, that's going to be my first substitution, equal the square root of y, so that means w squared equals y. Also, dw with respect to y, take the derivative with respect to y, is going to be 1 over 2 square root of y. Okay. So now when I make that change, I get x equals square root of y on top, that's a w, dy here, so this, by the way, implies that dy is 2 square root of y dw, which equals 2w dw. So I get a 2w dw up here for that. And then I have the square root of 2a minus y on the bottom. So 2a, can't do anything with that, minus y, which is w squared. So there we go. Now I'm not worried about integration limits right now because then I'll just add constant. I just want to show you the general solution here for this. So now I have this, which is rewriting it. I'll pull the 2 out, I get a w squared dw, square root of 2a minus w squared. So whenever I see something like this, a square root of something on the bottom with dw here, w squared down here, I think of trig substitution. So I draw a little triangle, and I try some things. So here's going to be my theta. I'm going to put w here. I'm going to make this side 1. So that makes this side, well, I can't make that 1 because down here this side would be 1 minus w squared, but I need 2a. So I'll make this 2a. So that means this side, because this side plus that side squared, this side squared plus that side squared has to equal that. So this will give me, so there's my little triangle, right? So if I take that side squared plus this side squared, it has to equal this side squared, and it does. Okay. So looking at that triangle, I want to convert things to trig functions. So w over this is the sine, so w is going to be, and let's see, this side over that is going to be cosine, so I'm going to get what else do I need? That'll probably do it. So I go up here to my integral. Let's move this up a little bit. And I get x equals my 2. Then I have w squared here. That is this squared, so I get a 2a sine squared theta. From this to, if I take dw with respect to theta, I get square root of 2a, derivative of sine theta is cosine theta. So dw up here is going to be this times d theta, so I get a and then divided by this down here, and that's equal to that. And see, pretty conveniently, the cosine thetas cancel out. 2a is a constant, I'll pull it out front, so I'll have 4a out front, and I have this. And this is an integral that you should know, but you could at least look it up. You know, usually what we do is do a trig substitution. So we'll put a cosine with a double angle in here for this. But I'll just write the results down for you. It's theta over 2 minus sine of 2 theta over 4. Okay, so the cosines cancel out, and then you get x equals this, where this is a well-known integral. You should know that. I'm writing down the solution there, is that. So this ends up with x equals 2a theta minus, the 4's will cancel here, but I'm going to leave 2a out here so that I'll have sine 2 theta over 2. So that is my x, and then if you go back to figure out what y would be, we would get y equals, go back up and look up here, y equals w squared. And what is w? W is this right here. So I get 2a sine squared theta. Or if you want to, you can write it, or you can write it 2a 1 minus cosine squared theta. So that's y.